Hello everyone, this is the first video of a series of 5 covering my presentation as a live instructor at University of Virginia. So our presentation today is on maps and geosciences. A little bit about me. I have a PhD in geology and I've been teaching geology since 2012. If you need to contact me, please use my University of Regina email address at zainab.azadbacht@uregina.ca. My office hours by appointment, and my office is the College West building at room 234.7. So, in general, why we do need to use a map in geosciences, there are a few answers to that. First and foremost is that the geological studies begins with a map. So as a geologist, you would go out, take a look at the outcrops and anything like geological characteristic that you're looking for, and you would take samples and create map. And this map would be the basic of your work. And in the future, anybody who wants to study the same area would use your map and any other map they can get their hands on to kind of like get as much information as they can from the same study area. And then we use the map to locate ourselves when we are going out in the nature. Plus, geologists and geographers use the maps to display several different types of information. So we can include geological, we can include topographical, and all the other sort of information on a map. So going through this presentation, I would be covering different aspects of creating a map, creating a cross section from it, and getting and extracting information from the maps that you may come across. So because I am teaching at University of Regina, I would use samples and examples from the Saskatchewan and University of Regina. So this is a geological map of the Saskatchewan province, and you can see that there are different information that you can get from the map. So first and foremost, each map would have a title, and then so you would see that it would have a title, it would have a scale on it, and then you would have a box that would be called a legend, and the legend would be representing any symbol, any color, anything that is used in the body of the map would be have a description in the legend. So if you're at any time using a map and you don't know what each color represent or what's like which symbol representing what, any information you would need would be in your legend. So I will be explaining a little bit about these in our future slides. So going through the scale, there are two types of scales that each map would have: horizontal and vertical. And this is a schematic figure just to show you what I mean by that. So when we go out and create a map, taking information from anything out in the nature would be having in both horizontal and vertical information. So take a building as an example. It would have a horizontal representation and a vertical representation. So as the horizontal representation, it would be this way, and your vertical representation is this way. So we cannot simply go out and measure something and map it because it's simply too big for us to draw it on our map. So what we use as geologists or as cartographer is to try to minimize it to the scale that we can actually put it on a piece of paper, and that ratio of making it smaller is what we actually use as a scale and what we represent on our map. So moving on to the horizontal scale. Horizontal scale, there are different types of horizontal scale that you can actually see on a map. First and foremost, there is a type of a scale that I didn't show on my presentation. So it's called a variable scale, and it's when you go out make a map, and it's between you and your colleagues. So it's a variable. So I would say when I create a map and I'm talking to my colleague or my friend, I would verbally say that, okay, this map has this ratio, like let's say 1 to 100 meter. and that's something between me and my friend, or me and whoever I'm sharing this information with. But when you want to create a map of a more official estate, you have to actually state the ratio of the scale on your map, and there are different ways to represent it. So the first one that you would see is called fractional scale. I'm sorry. So the fractional scale actually have a value of 1 to a number, and this 1 here, it actually tells you 1 unit on your map is equal to this much on the actual surface. So the unit to the two sides of the fractional scale is going to be the same. So if the left is on meter, the right is also on the meter. And because now you have two units divided together, the actual fractional scale is going to be a unitless limit. So and then following that, another way that you can represent the scale on a map is a graphical scale. And the graphical scale is when you see these lines on a map. So if we go back to our uh, map of Saskatchewan, the geological map of Saskatchewan, you can actually see that they have a graphical scale here. So what does that actually mean? When you see that, if you measure the line, let's say that our line is 15 centimeter on the map, and then when you actually read the value, it says 200 kilometer. So it means that 15 centimeter on this specific map would be equal to 200 kilometer in nature. There are different types of maps and different scales. So just to cover the basics, there are two different types of scale that we have on a map, either a large size and a small scale. So when we say a small scale map, it's so just taking Regina and University of Regina as an example. So when we talk about a small scale map, you can actually see the area of Regina. So it's basically covers a larger area, and but it contains a smaller amount of details. So if I actually looking at this map of Regina, I cannot see the University of Regina. But now, if I start to zoom in on a part of this map to find University of Regina, I would create a larger scale map that would cover a smaller area, but at the same time, it would also contain a larger amount of detail. So depending on which one would work best for you, you would create a map. And sometimes you need to convert values from one map to the one scale to another scale to get more information. So let's just give it a try and calculate a surface area. So let's say you have a map that it has the scale of 1 to 2000, and we're just using a meter here just to be easier. So how much on that would equate with distance on a 1/10,000 map? So if in general idea, the units to your scales are going to be the same unless otherwise stated. So now that I haven't mentioned anything about the units on these maps, let's just take meter as the scale and the value, the unit value. So if the left side of these two are 1 and they are equal, so we can write it like that. So that 1 centimeter, let's say 1 meter, 1 centimeter on my map is equal to 2000 meter on the actual map, on the actual surface. So what would that be on a 10,000 meter scale? And then so we're just doing the basic mathematic, and then 2000 to x equals to 10,000, and then you divide that to get the x value, and then you have the 5. So if 1 centimeter on a 1/2000 map is going to be 5 centimeter on a 1/10,000 map. So yes. And then you also need to know how much, like how to convert values. So sometimes you might be asked to change a centimeter to a kilometer or the other way around. So just to give you an idea, 1 kilometer is going to be 1,000 meter. Each meter is going to have 100 meter in it, 100 centimeter in it, and then it would be 1 kilometer would equal to 100,000 centimeter. So moving on, we also have a vertical scale on our map. And the reason that it's important to us is to actually represent any vertical information and vertical dimension that we have on our actual surface. So now let's think that if you have a really tall building right beside a really like like let's say take 1 story building to a 10-story building right beside each other, and you use the same vertical scale, when you start to map it, you would not be able to, because they affect each other, you cannot show the difference in the height. So because that's the height difference is something that sometimes could be important to us, especially when you're looking at the profile of something. We came in an idea to create something as vertical exaggeration. So vertical exaggeration is, okay, sorry about that. So vertical exaggeration is when you use a ratio to magnify the difference between the vertical differences between different material on your profile. So the horizontal and vertical scale must have identical unit, and then to create the vertical exaggeration, I mean, and then vertical exaggeration is a scale that is used to in order to emphasize the vertical features that you see on any given cross section or kind of like vertical profile that you create. So there is a formula to actually calculate a vertical exaggeration. So vertical exaggeration abbreviation would be called VE, and it's a unitless uh, value. So to actually calculate the vertical exaggeration, you have to divide the horizontal scale to your vertical scale that you have on a map. The picture in the figure in the left just is to show you an example of what I mean by when you have two difference of the um, vertical values on one profile. So just to give you an example, the first figure here, you can actually see that you cannot see a much difference in the vertical variation on this profile using just 5x or 5 times of the reality. Now, if we actually increase the exaggeration to 10x, you can actually start to see there's a difference. You have a like kind of like a taller feature comparing to this one on the left. And then moving on, if you actually increase it to 40 times of the what you're actually having as the vertical scale, now you would be able to kind of like differentiate and see the actual variation that you have in your elevation. So that's what I mean by vertical exaggeration. So that's something that can actually be really handy when you are creating a map and a cross section to show the differences that you would see on the surface. So let's give it a try. So the vertical exaggeration formula was to divide horizontal scale to vertical scale. So just to give you an example, the horizontal scale is going to be 1 to 50,000 and the vertical scale is 1 to 1,000 scale and meter scale. So to calculate the vertical exaggeration, we simply divide 50,000 to 1,000 and the vertical exaggeration is going to be 50. This figure here is again to show you another example of not using vertical exaggeration on a cross section and using it. So by not using any actual or a really small exaggeration, going through line A to B, you can see that there is not much a difference here on the using the same vertical scale. But now if you actually increase it and give it an exaggeration, you would be able to see the topography on your cross section. So what do we mean by topographical maps? So topographical map are the maps that they would summarize the difference, the value, the like the difference that you have in elevation on the surface. So on the left, you can actually see an example of a topographical map just to give you an idea of how it would look like in reality. So the first thing that it would catch your eyes on this map are these brown lines that you can see going through your map. And they are getting together really narrowly spaced in some localities, and they are far spaced in some other localities. So what are they and what they are representing? So these lines actually called a contour line, and each contour line represent uh, the same elevation. So basically a contour line is a line that would connect the points that have the equal elevation on a topographical map. So if let's take this line in here as an example. For example, let's say this is 100 meter of a contour line. That means that any given point on this line would have 100-meter value. No matter how far it goes, it would still have 100-meter value. So two consecutive contour line on a topographical map would have a limited distance. So, and that's the what we call a contour interval, or CI as an abbreviation. So, and the contour interval remains constant throughout your topographical map. So if a contour interval in a map is 200 meter, it would be 200 meter all the way through your map. So let's take this map as an example. I have 7300 here. Going to this one, it has 7400. If I go later on and figure out, the next one is 7800, and then I have the 7900 in here. So looking at these two, and in between of these two I have 5. So I believe that the contour interval between these lines are 20 meters, because there are 100-meter difference between these two, and I have 5 in between. So I believe that the contour interval for this actual map is 20 meter in between these contour lines, and it would be the same throughout your map. So looking at this map, you can actually see that there is a place that the contours are getting really narrowly spaced. So what does that actually represent? It tells you that you are facing a really steep slope. And then if you actually looking at the other areas when the contour lines are getting apart from each other, it represents a gentle slope. So if you ever get lost and you had a topographical map with you, and you were anywhere close to here and someone tells you to go left, you can actually tell them, no, I'm not going to take that way, because further on I'm going to get to a really steep slope that I might not be able to pass through it. But going to the right, or to kind of like to the south and southeast, you would be able to walk through it because it's a shallow and gentle slope. Okay, another thing that we have to cover about the topographical map and the contour line is that the contour lines actually react to when they pass through a river or a stream or a body of water. So if they actually when they pass through a river, so taking this river as an example, the contour line actually makes V when it passes through this river. And the direction of the water flow is always toward the open side of the V. So the direction of the water would be to your northeast. If you ever got confused of where the water is actually flowing by looking at the contour lines and using the V, I forgot what is the direction of the water, what you can do, you can actually check the elevation of the contour lines, knowing that water would not flow uphill. So let's take an example. So one of the lines that comes from the close side of the V has the elevation of 6600, and then this line, the contour line on the top, has 6278. So that's another indication that the water would flow this way. Now let's contour and map together. So remember when we were a child, they would give us a series of dots to connect and create a shape or a figure that actually comes handy when you become an adult and decide to be a geologist or a cartographer. So these are just simplified topographical map to show you how you would actually create and contour a map. What you have to remember is that any given contour line would have the same elevation going through your line. Basically, it would connect the same elevation to form. You would basically connect them to create a contour line. And remember that contour lines never cross each other and they form V when they pass a river. Knowing that, this is just a plain one to give you an idea how it would look like. So the first line that we can actually create in here is the 0, 1. So let's connect the 0, 1 and create the first contour line. Again, this is just a simplified, oversimplified to be honest, topographical map. So the next one we can actually create is the 100 line, connecting the 100 values. So this is a line that connects the 100 meter values, and the third one actually that we can actually create is the 200 one. Something you have to remember is that after you're done contouring any line on your topographical map, you have to label it. So the first one is 0, the second one is 100, and the third one is 200 meter value. Moving on, now that we are done contouring our map, we can create and construct a cross-section from it. So what do we mean by a cross-section? So you can have any given line. So this AB can be at any location on this topographical map. So basically, when you're using cross-section and creating a cross-section, that gives you kind of like you cross it and you see it from the side. It gives you a better look at the topography of your contour lines. So it basically becomes 2D rather just being a flat surface for you to see how elevation varies at that specific location. And if you are a geologist and you have the rock boundaries and rocks inside your topographical map, it also shows you how the boundary is changing, how like geological features are changing on that specific line. So the first step to create a cross section is to locate any place that the cross section line would actually passes a contour line, and locate those. So if moving from A to B, any place that I have the red circle is the place that a contour line would passes my line of AB. After you know exact location of this, you can move on to actually create your cross section. The next step is gonna be to know your vertical scale, or if you want to use a vertical exaggeration, you have to know the vertical exaggeration. So you would have a series of parallel lines with the values that would indicate either your vertical scale or the vertical exaggeration. So let's say mine is at 10 meter. I decided to go with 10 meter. So I have a 0, 10, 20, 30, 40, and 50. Now moving on from line A to B, moving on from A toward B, the first contour line that my line hit is the contour line of 20. So the value of this line is going to be 20. So I'm just bring it down to my lines and I hit the 20 and I stop. So I just mark at 20. Moving on, the next one I have is a 30 meter value. So I just bring it down and I stop at line 30. Moving on, there are two at 40, so I just bring them down and I stop at 40. I do the same exact thing going all the way through to B. I hardly recommend you to check after you're done bringing all the elevation down to your cross section, just to make sure that you have brought everything down. After you're done doing so, you would be left with a series of dots on your cross section profile, and the next step is to connect them with a smooth line. Now using this exaggeration that I had, you can actually see the profile. So looking at the topographical map and just see two hills in 1D, now I can actually see that how the elevations vary between these two. So now just to remind you, there are four major directions. You have north, you have south, you have east, and you have west. If someone told you northeast, it's between the north here and between the east, so that would be northeast, and the same for the rest of them. So now, as geologists, we also have rock boundaries. Now let's try to bring down a rock boundary to our profile. So let's take this line, the red line, as an imaginary rock boundary between, let's say, limestone and shale. And this is the place that it actually hits my line AB. So you would bring it down the same exact way that you brought down your contour lines to the profile. But in this one would not carry any elevation value to it. You just bring it down to the outer rim of your profile and it hits your line right in here. So now, in reality, you would have a deeping angle for your rock boundaries or any boundary you would have in the nature. So let's take 45 degrees to the east as a dip, just an example. So knowing 45 degrees to the east, now you can actually have a horizontal line that represents east-west here. Put your protractor on it and it starts to read 45 degrees from the east. So after you read 45 degrees from the east, now you can actually bring down and connect this. So you would just create a line that would carry 45 degrees to the east value. And that is the rock boundary between your shale and between the limestone and the shale. So in reality, you would most definitely have more than one rock boundary, and they might have different deeping values, but how you would actually bring them down is the same exact thing. So now you're almost done. You have contoured your map, you have created a cross section, you have carried on copying the deep value of the rock boundaries, and you've carried over your rock boundaries. Now what you have to do is to title your cross section. You have to give it a direction. You can either leave a north arrow or the right east and west direction on your cross section, so that the next person who comes across your cross section knows the direction that to look at for your map or your cross section. You have to add a legend, so any symbol that you use in your map should be in your legend. So the rock symbols, if you have a fault, if you have a rock boundary, if you have a river, anything that you use in your map should be in your legend. And also on a scale. So if you and remember that we have two, horizontal and vertical. So, and if you have a vertical exaggeration and you feel like that the next person should be aware of it, you can also indicate that on your map. So for my student at University of Virginia, we use this map as the example to create a cross section and to do a contouring. So I decided to change this 97 value to 105. So if you're seeing this, you can use 105 instead of 97. And these are the rock symbols to use for the rocks that you see in here using your assignment. So these are the symbols that you have to use for limestone, shale, and siltstone on this specific map. Meanwhile, if you are watching this and you're not a University of Virginia student, please feel free to contact me. You have my email at the beginning of the presentation. You can email me if you have any question or concern, and I would be more than happy to help you. Have a great day, and thanks for watching.